All right, well, we are going to keep moving back into chapter 8. We're almost done with 8.5, so plan is to get done with 8.5, 8.6 today, and then 8.7, 8.8. I'm gonna warn you, I won't be here on Thursday, so we won't have class Thursday. If you want to look ahead and do stuff, that's fine. But that probably means 8.7 will be due next week rather than this week. Okay, so just, we're coming down to the end of chapter 8, so we'll get moving with it. Okay. All right, so yeah, I'll try to send out an email too, just to remind you of that. So anyways, section 8.5, we've been dealing with, it's in alternating series. And remember that alternating means we're bouncing back and forth between positive and negative terms in our series. And we have this really nice convergence condition. As long as the individual terms, when I take the positive part of the individual terms, as long as the limit of those terms is 0 and those terms are decreasing, then the alternating series converges. So as long as the terms are decreasing to 0, when I take the absolute value or when I just take the positive part, then we converge. The other thing that we saw last time was what it meant to actually be absolute convergent versus conditionally convergent. Absolute convergent means that the series converges, and also if I take the series with the absolute value of the individual terms, that also converges. And then conditionally convergent meant that the series converges, but when you take the absolute value of the terms and create a series out of that, it diverges. So that was conditionally convergent. Notice that if our terms are always positive, then convergent means absolute convergent. So what we've been doing in 8.2, 8.3, 8.4, we typically had positive terms. And so we were just saying converge or diverge because there's no such thing as conditional convergence if our terms are all positive, right? It's either one or the other. And we looked at a couple of examples of that. Now, one last thing. That's nice about alternating series. So we've seen that alternating series have a really nice convergence test. We understand conditional versus absolute convergence. But another big benefit of alternating series is that alternating series will have a way to approximate the sum when the series converges. All right. So there's an easy way we can approximate. And I'll give you the specifics in just a moment. But I like to start out with an example. So let's take an infinite series. And this will be an alternating series, -1 to the n plus 1 divided by n squared. And we're going to expand that series out, and then we're going to approximate with that series. And we'll approximate this sum to within 1/25th and to within 1/50th of the real value. Okay. By the way, 1/25th, that's like 0.04. So we'll be within 0.04 of the real value. And then 1/50th would be 0.02. So we'll be within 0.02 of the real value of the sum. Okay. So that's what we'll do. Like I said, this theorem is going to make more sense instead of me just giving you the theorem by doing an example first. So if you put in n equals 1, the first term that pops out is 1/1. If I put in a 2, this becomes an exponent of 3. -1�3 is -1. And then with a 2, the denominator becomes 4. If I put in 3 for the third term, I get a +1 on top and a 9 on bottom. Everybody see the pattern? The denominator is being squared and the numerator is jumping back and forth between -1 and +1. Every time we have an even, we have a -1 in the numerator. Every time we have an odd n, we have a +1 in the numerator. Now, I'm doing this way more than I need to try to show the point, okay? I'm expanding this out more than I need. Now, let's just make some observations here. Let's say I look at the sum of the first 5 terms. Okay. Or actually, let's do the first 4 terms. Is that okay? I want you to examine remember the partial sum of the first 4 terms we denoted earlier, like way back in 8.2, is S sub 4. So S sub 4 is that. I guess I can calculate it. I got about 0.7986. I'll round it to 4 decimals right now. I guess I could try to make that into a fraction. 115 over 144 as a fraction. Okay. So that's partial sum of the first 4 terms. Now, I want you to think about whatever this limit is, maybe I should have said this earlier, but this is one we've seen earlier where it does converge. So I should have probably led with that this infinite series converges through the alternating series test. The terms are decreasing, if I look at just the positive, and they're decreasing towards zero. So it does converge. So the series, since it converges, let's say it converges to S. Again, I'm using the same notation I did back in 8.2. Right, if the limit of the series is, limit of the partial sums is equal to S, then we say the series is equal to S. Right? Now, here's the thing. We want to ask the question, how far is this partial sum away from this? What is the difference between what the actual series adds up to and a partial sum like S4? We'll call that R sub 4. Basically the remainder. Is that all right? So we'll call that R sub 4. And I want you to notice that if you take this infinite series and you lop off S4, all you're doing is you're taking off this first 4 terms, right? So what you're left with is this whole thing. That's what the R4 is. You don't have to write that down right now, but I'll write it down over here. R4 is 1 over 25 minus 1 over 36 plus 1 over 49 minus 1 over 64 plus 1 over 81. And so on and so forth. Now, here's what I claim. I claim that R4 is between 0 and 1 over 25. That the remainder here, I'm going to write it in absolute value, although we wouldn't have to in this example. But in general, if this term was negative, we'd have to use absolute values, but this term's positive. Now, why do I know that? Or how can I tell that? If you look at pairs of terms, 1 over 25 is bigger than 1 over 36 in absolute value. So if you paired up the terms this way, 1 over 25, 1 over 36, This would be a positive, a positive, a positive, and a positive, right? The reason we get that is because one of the key features about alternating series which converge is the individual terms go to zero, right? When we are we want those individual terms to go to zero in terms of absolute values of the terms. Everybody understand positive? So we have positive numbers that we're adding up all the time. So if I'm adding up a bunch of positive numbers, it has to be above zero. Right? Now, let me go the other way. This is 1 over 25. If I pair up numbers this way, I get negative, 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 plus 1 over 25. Everybody see that? So I get 1 over 25 plus a bunch of negative things. So that means it has to be less than 1 over 25. Okay. Every alternating series where the individual terms are decreasing in absolute value is going to work like this. That the remainder, after you lop off the first 4 terms, in absolute value is going to be between 0 and whatever this term is, whatever this 5th term is. Does that make sense? So let's talk about what that means. This means S4, which we said was 115 over 144, which we go to about 0.7986, is within 1 over 25 of the actual infinite summation. Right, since the difference between the summation and S4 is between 0 and 1 over 25. Okay. Does that make sense? So we have this nice way of approximating. And we say, well, if we want to approximate, let's say, so that's approximating within 1 over 25th. Now let's approximate to within 1/50th. So to approximate within 1/50th, what we do is we go to our alternating series and we wait until the fractions turn equal to or less than 150. Okay, follow that? So I would go to this stage right here, because this fraction is bigger than 1/50th. And this fraction is smaller than 1/50. That makes sense? In absolute value, if I'm not being clear about smaller and bigger, I mean in absolute value. Obviously. So to approximate within 1/50th, we use S7, since the absolute value of the 8th term is 1/64th. I should maybe say this way. Maybe rephrase that. Yeah, so 8th term is 1/64th. An absolute value. And that is smaller than 1/50th. And the absolute value of the 7th term is 1/49th, which is bigger than 1/50th. Okay. Now, S7 gonna be some ugly number, but you can calculate that. I'll give an approximate. I got 0.8312, something like that. Roughly. And the remainder, technically this remainder is gonna be negative because we start with a negative this time, -1/64. So if you wanted to say the remainder after 7, again, technically it's between 0 and -1/64. But what we usually say is that our remainder in absolute value is smaller than 1/64. And because we're dealing with absolute value, sometimes we just leave off the 0 as well. Okay. And that's less than 150. Does that make sense? Does it make sense why we can approximate this way and say, oh yeah, I therefore know that, well, I know even more. I know that my infinite summation is going to be within 0.02 of this number. All right. And that gives me a very good approximation. And we can always do this if we have an infinite series, which convert an infinite alternating series, which converges. And we have decreasing terms, right, in absolute value. By the way, this only works for alternating series. You can't do this if the terms are all positive, because we don't have that trick where we can pair them up and say, well, you know, these two are negative, these two are negative, those two are negative, et cetera, et cetera. Does that make sense? So if I cut it off here, we go negative, negative, and then we just do the infinite pairing. So we know it's going to be negative below zero, right? Our remainder is below zero. And then if I look at 1/64, keep that steady. That's a negative 1/64. And then this is positive, 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 so on and so forth. So it's a negative 1/64 plus a positive number. So we get that. Any questions about this? How to do it? All right. So that's how we approximate a sum to within 1/25th of the real value of what the sum should be. And how we could approximate that sum to within 1/50th of the real value. This is one that we saw last time that converged. This was an alternating series that converged. And so I want you to approximate this sum to within 1/5000. Try this on your own. All right. As I do this, the way I do it is I notice that the top, the numerator is alternating, denominator is in factorial. So I always just start with a 1, and then times 2, you get 2, times 3, you get 6, times 4, you get 24, times 5, you get 120, times 6, you get 720, times 7, you got 5,040, times 8, you get 40,320, times 9, you get 36,880. And then if I times that by 10, I'd say, well, my last one was a minus, that's the alternating, so this one will be a plus 1 over whatever this is times 10. And it turns out to be about over 3 million anyways. Okay. So that's kind of how I go about that. Now, if I want to approximate within one 5,000, I'm going to go up to the place where my next term is less than 1/5,000 in absolute value, which is right here. So what I'm going to do is I'm going to sum up the first 6 terms. All right. Because the 6th term is 1 over 720, but the 7th term is 1 over 5,040. Okay. And then I get an approximate for S6. I'm not gonna write, I guess I could write it. -1 plus half minus 6 plus 24 minus 1 over 120 plus 1 over 720. And I'll approximate that. I haven't calculated that. I should have probably done that before. But I didn't type that in my calculator yet. I got negative 0.6319-ish. I don't know what Moodle will ask you to round it to, but I know that's the case. And by the way, this is within 1/5,000 of the actual sum. that all right? So that's within 1/5000. By the way, 1/5000 as a decimal is like 0.0002. So if somebody came back and said, well, actually, I think the sum is 0.7, you'd say, nope, it's gotta be at least somewhere between negative 0.6319 and negative 0.6317, I guess. 121, 0.6321, you know what I mean? So within 0.02 of that number. And in fact, we know the remainder is gonna be -2, so it's gonna be a little bit less than that. Is that all right? Now, I want to point out something. This is why I kept the original series on the board. If I had to approximate this one to within 1/5000, it would have taken me quite a lot of terms, right? To get out to a place where 1/5000 is smaller than my term in absolute value. Here, within factorial in the denominator, we got to 1/5000 pretty quickly within the first 6. And then the 7th term was less than 1/5000 in absolute value. So that is one of the things here that if you want to approximate a series to within 1/5000, some series might only take you a few terms to do that. Other series might take you lots and lots of terms to do that. Just, it depends on how quickly our terms go to 0 in absolute value. The quicker they go to 0, the better approximation we have. The longer it takes to go to 0, it's gonna take a little bit longer. You're gonna have to have more terms. Does that make sense? I want you to try this on your own. Try to approximate this infinite series within 1,000th. This is again an alternating series. in this case, if I want to approximate within 1,000, and by the way, 1,000 is basically the third decimal place, right? Notice I can do that by just using S sub 2, the second partial sum. And that's because the second term in absolute value is 1/224, which is greater than a 1,000th. And the third term is 1/1701, which is less than 1,000. And S2 is about 0.1384. So what's this gonna be? Well, my actual summation, I could think through this, but it's gonna be within 1,000th of this number. So it's gonna be somewhere between 1.37 and 1.39 roughly. And if we're a little bit more careful about this, we could actually say, notice that the remainder, since it starts with a positive number, is going to be positive. And so it's actually going to be slightly above this, but not by more than 1,000. Okay. In fact, not by more than 1/1701. That make sense? Now, this is how I always think through the approximations. Okay, I just write out the terms, and then once I hit my mark, if I'm trying to approximate within 1,000, once I hit this next term, that an absolute value is less than 1,000, then I know I can stop. I know I kept writing a couple extra, but I know I can stop here. And so each time that I'm asked a question like, how do we approximate, use S2. And then I'll come up with the summation of what S2 is, and that's a good approximate. That's going to be within 1,000. So I write it out like that. If you read along in the book, whoops. There we go. This is called the alternating series remainder theorem. So it says, if I have a convergent alternating series where the terms are decreasing, remember those are the positive components of the terms. So the terms are decreasing. Then the absolute value of the remainder involved in approximating the sum by the nth partial sums is less than or equal to the first neglected term. That just means that how much the actual sum will be off from the nth partial sum is limited by the term a sub n plus one. That's exactly what we've been doing. It's kind of confusing wording. It's a little bit more confusing than it needs to be. But it's just saying as long as our terms are decreasing in absolute value, then our nth partial sum is off from the actual sum by at most the next term in the sequence. Does that make sense? So this is the alternating series remainder theorem. I like to use this. I like doing what I was just doing, writing out the summations and then saying, well, at this point is when we can cut this off. And again, I gave you examples where it didn't take many summations to get within 1/50th. In the example 5. In example 6, it didn't take a whole lot of summations of terms to get within 1/5000. Example 7 didn't take a lot. I could approximate by the second partial sum, right? And some series, it might take a really long time to get within 1/1000. All right? It might take a partial sum like S of 200 to get within 1/1000. You know what I mean? So obviously, it might take a lot of terms in some cases, but you do eventually get there. Okay. Any questions about that? Well, that's the last part of 8.5 that we are going to cover. We already covered the absolute versus conditional convergence. Now, before I move on to 8.6, I did want to mention, interestingly enough, way back in 8.2, where we had some interesting sums, a couple of these you could actually have approximated using the alternating series test. But a couple of these you could not. Like this first one, 1 over n factorial, you could have not used the alternating series test because that's not alternating. And you can't use this alternating remainder theorem because it's not alternating. But this one, where you have an alternating over n squared, we could have actually shown that you get really close to pi squared over 12. That was the series that we were actually dealing with, right? And if you look back, if you just hit pi squared over 12 in your calculator, you get 0.82246, blah, blah, blah. Remember, that's within 0.2 of, or that's within 1/50th of the decimal we got. The decimal we got was like 0.83, something or other. Does that make sense? And then this one, you could have also used alternating remainder theorem for that. Okay. So I just wanted to point that out, that couple of those things that we saw way back in section 8.2. We could have approximated using this alternating series remainder theorem. Okay. Everybody good with that? All right, now here's where some rubber meets the road. We're gonna deal with power series. Okay? And 8.6 covers power series. The way I think of a power series is think of it as an infinite summation or an infinite polynomial. So here are two different sort of infinite polynomials, f of x and g of x. We have 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and so on and so forth. And then we have g of x, which is 0 plus 1x plus 2x squared plus 3x to the third plus 4x to the fourth, and so on and so forth. Okay. And with both of those, we can write those as an infinite summation. So it's going to look like an infinite series with variables raised to powers. Does that make sense? And that's what a power series is. If x is a variable, then an infinite series of this form, just like the couple I had on the board, is just an infinite series with a variable part, and usually that's written as x to the nth power. Now I'm going to start my summation at 0, and that'll allow us to have a constant term. Does that make sense? On our polynomial. So it'll allow us to have a constant term. This is a power series that is centered at 0. We'll talk about what I mean by centered at in just a second. But again, it's this infinite polynomial. These are both centered at 0. If I want to center my power series somewhere else, so if I want to have a polynomial centered at, let's say, C, all I have to do is replace my x with an x minus C. We'll talk about why you would want to center at different values. And the basic of it is that if you want to approximate around a certain value, like let's say close to the number 3, then it's best to center it at 3. if you want to approximate close to where x is 14, then it's best to center it 14. And so on and so forth. So we center it at around the values that I want to approximate with. Now, the big question that we're going to look at is what values of x can I plug in and have that power series converge? So when I plug in a certain number for x, does my power series converge or does my power series diverge? By the way, notice that when you plug in a number for x, we get an exponential growth right here, right? X minus c to the nth power is an exponential growth when I plug in a number for x. But also, I have this coefficient of a sub n, and those a sub n's are not constant. They could be, it's going to be a various different sequence, right? Could be any sequence. So what numbers can I plug in for x and have the series converge? Well, it's obviously going to depend on the power series itself, which depends on where the center is at, and also depends heavily on the sequence a sub n. That makes sense? So it's going to depend on things. But we are going to have three options. Our three options are going to be the following. The power series is going to only converge at the center. That's one option. So option one, the power series only converges when you plug in the number c. And by the way, if you plug in the number c, what's going to happen? All of these just become 0, right? All these values become 0. If x is c, you get c minus c, which is 0 raised to the nth power, which is just zeros. So you get a bunch of zeros. So one option is it only converges when x is the center. Another option is that it converges for all real numbers. You can plug in any x you want to. So that would be the second option. And then the third option, which may be the most interesting, is that it converges within a range of numbers. There's something called a radius of convergence, where if we plug in an x value within that radius, it converges. And if we plug in an x value that's outside that radius, it diverges. So those are my three options for convergence. One, it converges only at the center. Two, it converges for all real numbers. And then three, there's this little section where it converges and it diverges everywhere outside of that section. There's this little section of the number line where it converges and it diverges outside of that section on the number line. Now, like I said, it's going to depend on that A sub n. So we're going to have to remember which types of growth overpower the other types of growth. And remember, n to the nth power is faster growth than n factorial. And n factorial is a faster growth than exponential type growth. And n to the p is a slower type growth than exponential. And natural log of n is a slower growth than exponential. You guys remember that? And when you plug in a number for x into your power series, this piece is exponential already. Do I see that? It's going to be some base to the nth power. So if this component has like an n factorial or an n to the nth power, it's going to overpower the exponential part. If this component only has an n to the p, then the exponential part is going to overpower the n to the p part. Does that make sense? So we already have exponential from our polynomial, x to whatever, x minus c to a nth power. So let's take a look at this example. And let's determine the radius of convergence of n factorial times x to the n summed up from n equals 0 to infinity. So n factorial is obviously factorial growth. X to the n is exponential growth. The n factorial is faster. So this series is going to do whatever the n factorial does, regardless of whether I plug in a value for x that's 25 or 1/25th, right? No matter what value I plug in for x, the n factorial is going to, what I call, dominate. It's the faster growth. It's going to take over. So n factorial will dominate the series. So this series is going to behave just like the x to the nth power doesn't exist. Right? This series without x to the nth power diverges. Everybody see that? Because the n factorial is in the numerator. We're just gonna be adding up bigger and bigger and bigger and bigger numbers. So this diverges. So this infinite series, n factorial times x to the n, will diverge as long as x is not 0. Because when x is 0, then I'm just adding up a bunch of zeros. Everybody follow that? Another way to say that is that this only converges when we have x equals 0, because that's the only time when x is equal to 0, we're summing up a bunch of zeros. Everybody get that? So this is the example that it only converges at the center. Right? Remember, this is centered at 0. So this only converges at the center. Everybody okay with that? Let's take a look at this next one. This next one's very similar. So I will go through it fairly quickly. What if we centered this at 2 rather than centering this at 0? Does anything change? The answer is no, not really, other than where the center is, right? So if we're trying to find where this converges for what x values, I'll just write it this way. N factorial will dominate. I know. Everybody get that x minus 2 is still x minus 2 to the nth power, that's still exponential growth. Everybody follow that? Still minus x minus 2, still exponential growth. So the factorial dominates the exponential. The factorial, when you sum it up, diverges. So there's 2 ways you can phrase this. This diverges whenever I have a non-zero number in here. So in this case, this diverges so long as x is not equal to 2. It only converges when x is equal to 2. And again, that's exponential growth versus factorial growth. Factorial growth is fast. Yeah.
So if you have an equation where factorial growth is dominating the series, will it always only converge at the center?
Not exactly. So let's look at another one.
what does it mean by center? Like, I understand it's like you're finding a radius, but I don't understand what that means, right?
So center just means that, center just means that when we take our, well, I can do this. When we take our infinite sum, we're gonna write it with x minus a number raised to the nth power instead of just x raised to the nth power. And that x minus a number is called the center. Okay, and the reason it's called the center is because if we get into this case, we'll see that the interval at where this converges is centered at C. So that's where the word center comes from.
Okay.
But all it is like, we're writing it as x minus C to the nth power.
Okay.
I don't know if that clears it up, but that's just the number. It's called the center, and it's called the center because when we get into this case, that's the center for the convergence radius. The radius of convergence,
Okay,
interval of convergence.
thank you.
So here's a good example of the issue you brought up about n factorial being in the problem. And what's happening here, okay? So n factorial is in the problem, but it's not gonna behave quite like the examples we did. By the way, this is centered at -1 because it's just x minus a -1 to raise to the nth power. So the center just means that, whatever that number is. Just a word we call that. So in this example, we have lots of different things, different types of growth going around. We have n is n to the p growth, specifically with p equals 1. X plus 1 to the nth power is exponential growth. N factorial is obviously factorial growth. And 3 to the nth power is again exponential growth. So we have a bunch of different types of growth all being multiplied. The factorial growth will dominate. It'll be the fastest type of growth around. By the way, dominate is not an official math term, okay? So if you're looking for that term in the book, it's not gonna happen. That's why I keep putting it in quotations. But what I mean by that is it's the fastest type of growth going around. Okay? And therefore, whatever is happening with these other things are not going to matter as much as where n factorial is. So whatever's happening here in my infinite series, it's going to behave like an infinite sum of 1 over n factorial. Now, n factorial I had to put in the denominator that time because it was in the denominator over here. and this converges. Right? And so what we're saying is, no matter what x is, since this converges, and the n factorial on bottom is going to dominate up here, it's going to behave like that. So this is going to converge regardless of what x is. So this is the example where we have an n factorial. And it's going to converge for all real numbers. So x can be any real number. And this series will converge. Now, usually I write this out in notes so you can kind of go back and see what's going on. But when you actually get into doing the problems, you just say, oh, n factorial dominates. It's like this, and it converges. Right? You don't have to write everything out every time, but it's good to have in your notes, just saying, oh, we're talking about n to the p growth, exponential growth, factorial growth, exponential. Factorial is the fastest. So whatever this series does, it's going to be dominated by the factorial. It's going to act like this. This one converges. So no matter what x is, that one's going to converge. Is that all right? And by the way, if you had an n to the nth power, that would dominate over everything else too. If you had an n to the p, not going to dominate over n to the nth power. N to the nth dominates over n factorial. N factorial dominates over exponential. Exponential dominates over n to the p. N to the p would dominate over natural log. Does that make sense? All right. So those are the two, like the examples where it either converges only at the center or it converges everywhere. Converges everywhere means I have an n factorial or an n to the nth power, and that is in the denominator, right? Now, let's check this out. Let's say we have an infinite series x to the n divided by just n. And we have to start at count of 1 and go to infinity. We have two types of growth going on. We have an x to the nth power and an n. Now that n is just n to the first, so that's n to the p type growth. X to the n is exponential growth. What's going to dominate, exponential or n to the p? Exponential is going to dominate, right? Exponential will dominate. So this series is going to behave mostly like an infinite series where I just have x to the n and I can ignore the n to the p. Now, this is in the numerator, so I have to make sure it's in the numerator. But it's gonna work like this. Let me rephrase this. So it's gonna work like x to the n. Well, for what values of x does this converge? Well, this is geometric. Remember, sum a r to the n, where r is equal to x, basically. And then just a is just the number 1 right now. Okay. In fact, if you want to erase the a and the geometric, you can. It's not a big deal. And in geometric series, those converge when r is between -1 and +1. In our case, that means x is between -1 and +1. So our infinite series converges when x is between -1 and +1. Here's the tricky part. It turns out outside of those bounds, it's going to definitely diverge. Okay? Do I follow that? So it diverges if x were 1.5, or if x were 2, or if x were 3, or x were 4, x were 3.8. Anytime x is bigger than 1, it's going to diverge. Anytime x was like -2 or -3 or -3.8, it's going to diverge. There is one place, though, that we haven't covered here, and that's the endpoints. Okay? At the endpoints, you kind of have to manually check them, each one. So at x equals 1 and x equals -1, we have to manually check. Everybody okay with that? What I'm saying there? Oh, wrong one, wrong button. So let's go ahead and do that. At x equals 1, our summation x to the n over n becomes a summation of 1 over n. Okay, see what I just did? 1 raised to the nth power is always just 1. So does that converge or diverge? This is a P series. This diverges. Right, this is n to the first. That's our P series. At x equals -1, I get -1 to the nth power divided by n. That actually converges because that's an alternating series where the terms are going to 0. So we're decreasing to 0. That makes sense? Everybody get why I have to plug in these things manually? The essence of it is that if I'm at those endpoints of 1 and -1, in this case, then my exponential piece kind of goes away. And then I'm left with some other stuff. So that's the idea. All right. So if I'm at the endpoints, then I have to go back and use my other tests to determine. Usually one of the endpoints is going to give you an alternating series, and the other endpoint is going to give you a series with either all positive terms or something like that. Okay. So one of the tests that we've been doing from 8.2 all the way through 8.5, is going to be applicable there. Okay. Let's do another example. Starts at n equals 0. That's so in example 5, we have x minus 2 to the nth power is exponential. And then 3 to the nth power is also exponential. So exponential growth is the only thing we got going on here. So the exponential growth is going to dominate. But since there's 2 of them, I have to treat them together as one exponential growth. Does that make sense? since there's two things with exponential growth, I'm gonna have to rewrite this series. So I have one component of exponential growth, so that I can see what my R is in the geometric sense. Does that make sense? All right. So. We have two exponentials, so the exponential growth dominates. If I had like an n to the second power or, a natural log of n lying around, I'd ignore those in this next step. And I'd say, well, therefore, this is like, well, this is exactly like. I'm gonna rewrite this into one big exponential growth. X minus 2 divided by 3, all raised to the nth power. And that's a geometric series with R equals X minus 2 over 3. We're okay with that so far? So R here is no longer just X. R is some thing that involves all of our exponential pieces. X minus 2 over 3 in this case. And we know a geometric series converges when R is between -1 and 1. Therefore, my series is going to converge when X minus 2 over 3 is between -1 and 1. Now let's solve this for X. We multiply all three sides by 3. And then I would add 2 to all three sides. So what are we saying? We're saying that our series converges when X is between -1 and 5. And diverges outside of those bounds. So if X is above 5, it diverges. And if X is below -1, it diverges. We're okay with that? And then the endpoints we'd have to check manually. make sense? So let's check those two. Let's check 5 first. At x equals 5. Five minus 2 to the nth power is 3 to the nth power over 3 to the nth power. That's just an infinite sum of 1, isn't it? Be okay with what I'm doing here? Just plugging in 5 in for x, seeing what you get. I get an infinite sum that's just adding up 1 over and over and over and over. That diverges because of the divergence test. Remember, if the terms don't go to 0, then the series diverges. I could put a divergence test in 1 and 2. Or you can put terms don't go to 0, either way. And then at the lower end point, -1. -1 minus 2 is -3 to the nth power over 3 to the nth power. It turns out you can pull out a -1 to the nth, and you get basically an infinite summation. The 3's will cancel out once you do that. You'll get an infinite summation of -1 to the nth. And again, this one diverges too because of the divergence test. So the terms aren't going to 0. Now, just so that we're all aware of the terminology here, okay? I had mentioned radius of convergence and center and things of that nature. So let's talk real quickly about terminology in this example. The interval of convergence is from -1 to 5. All right. So if you ever hear about the interval of convergence, we're talking about from -1 to 5. You could write that in interval notation, but I'll write it just that way. Okay. The center here is 2. And notice that that is right the middle number between -1 and 5. Okay, so the center is 2. And we knew that because we said the series is centered at 2. And it's always going to be the case that if our series is centered at 2 and we have an interval of convergence, then the middle of that interval of convergence will be 2, or the center, whatever it happens to be. Okay, that's where the term center comes from. And lastly, if somebody asks you for the radius of convergence, the radius of convergence is actually 3. It's the distance from the center to either side. Okay? So the radius of convergence is 3 here. In our previous example, our interval of convergence was between -1 and +1. Our center was 0. And our radius of convergence was 1 in our previous example. Does that make sense? I'm not going to we're not really super focused on terminology, but if I'm using those terms, I just want you to know what those are, okay? All right, interval of convergence is where we converge. Center, this number, or it's the center of our interval of convergence if we have an interval of convergence. And our radius of convergence is, in this case, 3. So some people will look at this interval and say, oh, radius of convergence is 6. That's not the case. Radius of convergence is from the center to the outside edges, not the total span of the interval. That's why I wanted to mention it. All right? Good. And this is basically what power series is. We're trying to figure out where things converge, where things do not converge. And we always say, well, if the exponentials dominate, create a geometric series with R being that exponential part. Geometric series converges when R is between -1 and 1. So whatever the exponential part is, has to be between -1 and 1. Then go through to see where your x's have to be. Okay. If the exponential part doesn't dominate, then we're in a case where we either always converge for all real numbers, or we always diverge except at the center. All right. Any questions about that? Well, like I said, I won't be here on Thursday. If you want to, you can look through some stuff or look through the future. But other than that, I'll see you next Tuesday. You'll also should get an email that says we don't have class on Thursday as well. Okay? All right. See you then. See you next time.